Last video I walked through the OWASP State of Agentic AI Security and Governance report, the most comprehensive picture we have of where Agentic AI security stands. Today the series continues at the top of the risk list. ASI01, Agent Goal Hijack, the #1 entry in OWASP top 10 for agentic applications. And this is not theoretical risk. A zero-click attack called EchoLeak quietly turned Microsoft 365 Copilot into a data exfiltration engine. Nobody clicked a link, nobody opened an attachment, a crafted email just sat in an inbox waiting for the agent to read it. Let me walk through what Goal Hijack actually is, why the goal-oriented nature of agents makes it uniquely dangerous, the real-world incidents behind the ranking, why prevention is much harder than standard advice makes it sound, and the mitigations that actually move the needle. If you are newer to AI and agents, stay with me. I will keep this accessible. First, the foundation, because this is where the risk comes from. A chatbot answers a question and stops. An agent takes a goal. You ask it to triage your inbox, research a vendor, or fix a bug, and it breaks the goal into a plan, chooses tools, executes steps, checks its own progress, and keeps going until it decides the goal is met. The goal steers everything the agent does for the rest of their workflow. That autonomy is the entire value proposition. It is also the attack surface. OWASP defines Agent Goal Hijack as the manipulation of an agent's trusted state or inferred objectives, causing it to pursue actions that diverge from the user's original intent. Notice what that means in practice. An attacker does not need to breach your network or steal a credential. They need to get words in front of your agent. If you already know prompt injection, here's the distinction that matters. Prompt injection is a technique. Goal hijack is the outcome. Inject a chatbot and you corrupt one response, which a human reads and can dismiss. Hijack an agent's goal, and every downstream plan, tool call, and memory write now serves the attacker's objective instead of yours. OWASP maps 5 ways in, spanning direct user input, retrieve content, tool outputs, other agents, and configuration files. Retrieve content is the most common vector and matters most for what comes next. Here's where it stops being abstract. EchoLeak, disclosed by researchers at AIM Security in June 2025, was a proof point. An attacker sends a crafted email containing hidden instructions. It sits dormant in your inbox days or weeks later. The user asks Copilot a routine question. Retrieval pulls that email into context and the hidden instructions take over. The agent gathers sensitive data, embeds it in an image URL that fetches automatically to attacker infrastructure. The user never clicks anything, never sees anything, and never knows. That is a goal hijack, with 0 clicks required and one of the most widely deployed AI assistants on the planet. And the state of report ties this class of risk to real incident data. It documents the espionage campaign Anthropic detected and disrupted, where AI executed 80 to 90% of tactical operations across roughly 30 targeted organizations. It cites CrowdStrike data, showing an 89% increase in AI-enabled adversary attacks, with an average breakout time down to 29 minutes. I covered this dynamic in my piece on cybersecurity's friendly fire problem. The attackers are already operating at machine speed. Let's talk about why prevention is harder than it sounds. The standard advice sounds simple. Treat every piece of natural language that reaches your agent as untrusted input. It is correct advice. It's also brutally hard to act on, and I want to be honest about why. Start with the scale of the problem. The attack surface is essentially everything the agent reads. The open internet, internal data, emails, Slack messages, tool outputs, and user inputs are all natural language channels into the goal. Google DeepMind mapped this in their recent research on AI agent traps. Manipulated content planted in the agent's environment and designed to hijack it. They described 6 categories of traps targeting every stage of the agent loop, and many are invisible to humans, hiding HTML comments, CSS, and image metadata. The web was built for human eyes, and agents now read it with very different ones. In large-scale red teaming, the researchers cite that every agent tested was compromised at least once. Traditional input validation works because code and data are separable. You can parameterize a SQL query. You cannot parameterize English. To an LLM, instructions and data arrive in the same channel, as the same tokens, and the model has no reliable way to tell the difference. Simon Willison, who coined the term prompt injection, puts it plainly. These models do not follow our instructions. They will happily follow any instructions. Willison also gave us the cleanest way to think about when this becomes dangerous. He calls it the lethal trifecta: access to private data, exposure to untrusted content, and the ability to communicate externally. Any agent that combines all 3 is one crafted input away from exfiltrating whatever it can reach. Now here's the tension I want practitioners to sit with. Those 3 capabilities are not a misconfiguration. They are the product. An agent is valuable precisely because it can read your email, search the web, and act on your behalf. Strip out data access and the external actions and you are back to a chatbot. Security and utility are pulling on the same rope, and every deployment decision is a point on that trade-off curve. And do not expect guardrails to close the gap on their own. Willison makes the point that a filter catching 95% of attacks is a failure in security terms, because adversaries iterate until they find the 5%. I dug into this in my piece on whether we needed CVSS for AI jailbreaks. And this scientist, Apostle Vasilev, published a peer-reviewed proof that no finite set of guardrails can be universally robust against adversarial prompts. That is not an engineering gap, it is a mathematical property of these systems. Meta proposed one of the more practical framings called the agent's rule of two. In any given session, the agent should satisfy no more than 2 of 3 properties. The first is processing untrustworthy inputs. The second is access to sensitive systems or private data. And the third is the ability to change state or communicate externally. If the job genuinely requires all 3, the agent should not run autonomously. A human approves the consequential step, or the contexts get reset before the risk compounds. I like the rule of 2 because it is honest. It accepts that prompt injection is unsolved and manages blast radius instead of promising prevention. But I want to be fair about its limits. The most valuable agent use cases are exactly the ones that want all 3 properties at once, so the rule forces uncomfortable product conversations. Deciding what counts as untrustworthy input or sensitive system is genuinely hard in a real enterprise, where data flows do not arrive neatly labeled. And Meta itself says the rule is a supplement to least privilege and defense in depth, not a substitute. Here's the part that concerns me most. Many organizations are not even getting this far. The State of Report found that shadow AI in nearly every organization examined, and 29% of the Fortune 500 are already paying customers of a single leading AI startup. Deployment is sprinting. These mitigations are jogging. The gap between the two is exactly where incidents like EchoLeak and others live. If prevention cannot be perfect, the control plane has to move to runtime. And this is where I would spend practitioner energy. 3 layers that matter. The first is intent analysis. The original user goal is the anchor, so capture it explicitly and compare the agent's behavior against it at every step. The guidance emerging around ASI.01 describes concrete techniques. Semantic similarity checking compares the declared goal against each planned action. Plan coherence analysis asks whether the current sequence of steps still serves the stated objective. The intent capsule pattern goes further and binds the original goal to the session, sometimes cryptographically, so actions that do not align get rejected rather than executed. The second is runtime observability. You cannot detect a goal deviation you cannot see. Log every action, every tool call, and the reasoning behind them. Baseline what normal looks like for each agent and alert on anomalies, like an inbox triage agent suddenly making outbound web requests. The third is runtime enforcement, and this is the one I would prioritize. These are hard boundaries that hold no matter what the model believes its goal is. Apply least agency, so the agent only gets the tools and the data the specific task requires. Enforce egress controls and tool allow lists and deterministic code outside the model. Require human approval for consequential actions like sending money, deleting resources, or communicating externally. One of the more promising directions here is dynamically governing the lethal trifecta itself. Some teams are pursuing taint tracking, an idea borrowed from decades of program analysis. The moment an agent ingests untrusted content, the session gets marked as tainted, and high-risk capabilities are revoked on the spot. The agent that just read an unvetted web page can keep reasoning, but it loses the ability to communicate externally until the context is reset. Instead of statically picking 2 legs of the trifecta up front, you let the agent's actual exposure decide which leg gets cut and when. For example, there's a research approach called CAMEL that works in the same spirit, tracking the provenance of every value flowing through the agent so untrusted data can never drive external actions. The principle to internalize is that the boundary must live outside the model. A hijacked agent will happily explain why the new goal is legitimate. Your controls cannot take its word for it. Goal Hijack sits at number 1 on the ASI top 10 for a reason. The goal is the agent's steering wheel, and we have handed the passenger seat to every email, web page, and document the agent touches. Notice too that deviation does not require an attacker at all. Agents drift from their goals inadvertently. Through ambiguity and error, the State of Report makes this point that once an agent can send the email, move money, or commit code, the same controls govern a benign malfunction and a deliberate attack. Build for deviation and you cover both. So treat all natural language inputs as untrusted, but do not stop there. Constrain the lethal trifecta statically where you can and dynamically where you cannot. Apply the rule of 2 honestly. Then invest in intent analysis, runtime observability, and hard enforcement boundaries because that is where the fight actually gets won. We will be working down the list in the next video of the series. Links below. Subscribe and I'll see you in the next one.